Hey everyone, let's dive right into this explainer and completely transform the fundamental rules of measurement. We're going to take this from a dry, boring textbook concept and turn it into your absolute ultimate physics toolkit. Today, we're looking at the very foundation of how we quantify the physical world around us. We'll explore the real boundaries of human precision, and, my favorite part, we're going to uncover a mathematical cheat code that physicists actually use to verify the secrets of the universe.
So you might be wondering, how do scientists all over the globe agree on what a kilogram or a second actually is? It's a great question, because without a universally accepted standard, every single physics calculation in the world would be total chaos. Just imagine engineers in different countries trying to build parts for the exact same spacecraft, but their rulers and scales don't match up. I mean, it would be a total disaster, right? To avoid that nightmare, humanity literally had to come together to establish a single, common language of measurement.
All right, here is our roadmap for today's masterclass. We are going to cover the universal measurement system, the rules of precision, math with significant figures, unlocking dimensional analysis, and finally, proving physics equations correct. Let's jump into section 1, the universal measurement system, building the blocks of the universe. This is the bedrock of all physical science. What you're seeing here is the modern SI system, which originated back in 1971 and got a major update recently in 2018. And what's absolutely wild about this is that it proves we only need these 7 base blocks to measure literally anything in the cosmos. Think about that. From the massive, mind-boggling scale of galaxies measured in meters, all the way down to the tiny electrical currents pulsing in your brain measured in amperes. These 7 fundamental quantities are the whole shebang. Every other unit of measurement you will ever use is really just a combination of these base 7. Okay, section 2, the rules of precision and why those trailing zeros actually matter. Let's be real for a second. Every single measurement we make involves errors. Absolute perfection, it's just impossible. There's always a limit to how precise our instruments are. So, significant figures are basically how we honestly report that precision to the rest of the scientific community. For example, let's say you're timing the swing of a pendulum, and you write down 1.62 seconds. Well, the 1 and the 6 are absolutely certain, but that final 2? That's kind of just an estimate. It's your first uncertain digit. So altogether, that gives you 3 significant figures. The crucial trick here is knowing exactly which digits actually convey real precision and which ones are literally just placeholders. If you have trailing zeros without a decimal point, they do not count. So, 12,300 centimeters, that only has 3 significant figures, the 1, the 2, and the 3. But if you have zeros trapped right in the middle of non-zero digits, like that 0 in 0.002308 meters, those absolutely do count. Also, notice how those leading zeros in the decimal don't count either? They're just showing us the scale or magnitude of the thing, not the actual precision. Now, this principle is an absolute lifesaver. It protects us from a super common mistake. Say you measure a length as 4.700 meters. That has 4 significant figures. Those trailing zeros after the decimal are placed there on purpose to confidently say, hey, my instrument is exactly this precise. But what if we convert that to millimeters? It becomes 4,700 millimeters. You might look at that and be tempted to say, oh, that only has 2 significant figures now. Nope. A simple unit conversion cannot magically destroy the hard-earned precision of your original measurement. And to avoid that exact confusion, physicists rely super heavily on scientific notation. Moving right along to section 3, math with significant figures. Or, as I like to call it, don't let your calculator lie to you. We need to apply these rules to actual math. Because honestly, your calculator is probably giving you absurdly precise lies. Let's look at calculating density, which is just mass divided by volume. If you have a mass of 4.237 grams, that's 4 sig figs, and a volume of 2.51 cubic centimeters, that's 3 sig figs, your calculator is going to eagerly spit out this massive string of numbers, 1.6880478, and so on. But guys, it would be completely absurd to claim that level of precision when your volume measurement was so loose. The rule is, when multiplying or dividing, your final result can only be as precise as your least precise original number. In this case, that's 3 significant figures. So we round it off to an honest density of 1.69 grams per cubic centimeter. But hold up, watch out for a massive trap right here. When you switch gears from multiplying to adding or subtracting, the rules completely change. Addition and subtraction care exclusively about decimal places, not the total significant figures. If you add 436.32 grams to 227.2 grams, your least precise measurement only goes to one single decimal place. So your final answer has to be rounded to one decimal place, completely regardless of how many total significant digits that leaves you with in the end.
Okay, Section 4, Unlocking Dimensional Analysis, the physicist's ultimate cheat code. This is where things get really fun.
This is the climax of our explainer, where physics starts to feel a little bit like reading the matrix. By stripping away specific numbers and units and focusing purely on the fundamental dimensions, which we put in these cool square brackets, we literally reveal the hidden DNA of every single physical quantity. Mass becomes simply m, length is L, and time is t. From there, we can map out anything. Volume, it's just length times breadth times height, so it's L cubed. Velocity is distance over time, so it's L times t to the negative 1. And force, mass times acceleration, becomes m times L times t to the negative 2. Now, this brings us to the principle of dimensional homogeneity. I know, it sounds super complex, but it's actually pure common sense. It basically means you cannot add velocity to force. It's exactly like how you can't subtract an apple from a galaxy. It just doesn't make sense. You can only add or subtract terms that share the exact same dimensional signature.
Which brings us to Section 5, Proving Physics Equations Correct, using the dimensional hack.
Let's see how this builds into an incredible tool for checking if an equation is actually valid. Let's test out the famous equation setting kinetic energy equal to potential energy. 1/2 mv squared equals mgh. Let's look at the left side first. Mass is m, velocity squared is L over 2 all squared. Simplify that and you get mL squared t to the negative 2. Okay, now the right side. Mass is m, gravity, which is an acceleration, is Lt to the negative 2, and height is L. Multiply all those together and boom, mL squared t to the negative 2. Look at how beautifully that works. Both sides match perfectly. Even if we didn't know the deep physics behind energy, we just proved this equation is dimensionally consistent, and therefore it's possible. Actually, scratch that. We do need to talk about the catch. We have to recognize the one inherent limitation of our cheat code. Dimensional analysis is brilliant at catching absolute garbage equations. Like if you proposed an equation where kinetic energy equaled mass squared times velocity cubed, the dimensions wouldn't match at all, and we'd know instantly it was dead wrong. But dimensional analysis is completely blind to pure numbers, fractions, and dimensionless constants like pi. Did you notice how the 1/2 from our kinetic energy equation just totally vanished during our check? If an equation passes, it's a fantastic sign, but it's not a 100% absolute guarantee of complete correctness. But wait, because here is the ultimate flex of dimensional analysis, actually deriving equations completely from scratch. Say you want to figure out the time it takes a pendulum to swing. You guess it might depend on the length of the string, the mass of the bob, and gravity. You set them up with unknown exponents, x, y, and z. By forcing the dimensions on the right side to match the pure time dimension on the left side, the math actually tells us that the exponent for mass is exactly 0, which means mass doesn't matter at all for a pendulum. The exponent for length is 1/2, and gravity is -1/2. By just looking at the dimensions, we derive the exact formula for a pendulum swing. I mean, what an absolutely incredible physics hack.
But remember, since pure numbers and constants have no dimensions, they slip right past our dimensional filters. In that pendulum equation we just did, the dimensions gave us literally everything except the true value of that constant k sitting at the front, which actually happens to be 2 pi, by the way. And so this leaves us with a pretty fascinating lingering mystery to ponder. If our dimensional cheat code outlines the skeleton of the universe so flawlessly, how do we eventually hunt down the exact, dimensionless numbers that these dimensions hide? Well, keep wondering, keep measuring, and I will see you in the next explainer.